leveraging the collapse of the ice shelves by seeping down through cracks and essentially breaking up the mechanical or weakening the mechanical fabric so that some other event, maybe a storm, maybe some sort of ocean surge, can cause them to catastrophically collapse. And the point about it is that over the last 50 years, that beige line has moved further and further south. It has to go a long way. We have to have a very substantial warming before we get anywhere near the major ice shelves of the Ronnie Filchner. And that's an important point to make. The bulk of the Antarctic ice is well below 0 degrees centigrade, and so is still, if you like, secure and safe. It just gives you a few statistics on collapsed ice shelves. Now, ice shelves float anyway, so they've already done their Archimedean bit by raising sea level. But it has been speculated prior to these collapses that they may hold back the flow of the glaciers that feed them. These little arrows here show that when Larsen A collapsed, the feed glaciers speeded up by about a factor 3. When Larsen B went, there was somewhere between a 2 and 6 times acceleration of the glaciers. But the glaciers south of the collapse area, where we've still got bits of the Larsen B left, haven't changed. So nature's done a very convenient experiment for us and demonstrated what people were speculating about, because the models, I'm afraid, aren't up to allowing us to predict exactly what would happen with any confidence, that if you remove ice shelves, the glaciers accelerate, and of course in doing so, they do increase their contribution to mean sea level rise. And overall, it looks like the peninsula is adding about 10% of the annual mean sea level rise that we see today, and that has increased as a result of these ice shelf losses. Looking at the Antarctic more generally, this is the Kurt Davis et al. Data from Altimetry using ERS and other altimetry over a decade or so. The hole in the middle is because the altimeters that these data are drawn from don't get further south than that. You can see over the bulk of what's called East Antarctica, the yellow and orangey regions, because a warmer atmosphere carries more moisture, there is more snowfall. That was expected. You can see that there's considerably more snowfall at the root of the peninsula. But you can also see some blue areas where there's some very, very substantial discharge. And in particular, if I just summarize that, so there's growth in the East Antarctic. There are major discharges on Pine Island and Thwaites in the Amundsen Sea embayment, which is on the left there. I'll show you an arrow in that. And then there are 1 or 2 areas in East Antarctica which are showing the same sort of behavior. So that area with the purple star on it is particularly important, but there are a couple of others that we need to keep an eye on too. Now, why are we interested in these? Well, 50 years ago, Mercer suggested that these marine ice sheets, in other words, ice sheets that sit on rock below sea level, and in some cases 2 kilometers below sea level, might be unstable to warming. Actually, it'll be an ocean warming, not an atmospheric warming. And that there could be some runaway positive feedback that once these things started to slide would allow pretty rapid disintegration. And really, on the basis of no evidence, that hypothesis came in and then went out of favor. But it's been revived by these satellite data, altimeter data, that show that it's indeed the marine bits of the ice sheet that seem to be doing something. Now, these are in areas where the air temperatures are very low, so the candidate for change here has to be changes in oceanography. We know that between the last glacial and the Holocene, sea level rise has run at rates at least an order of magnitude greater than those that we see today. So we know that when ice sheets go, they can go quite quickly. And just to remind you that there was 120 meters of sea level rise over that period. But I've filched this very nice little overhead from Bob Binshadler, who showed it at the Antarctic Treaty Meetings in Edinburgh last week. This is a comparison of the Vostok record of temperature running from left to right over the last 400,000 years, and a record of mean sea level rise. And to guide the eye, if I can put that in, Bob makes the important point that although latent heat diffusion of ice is or snow is whatever it is, and initially it's not obvious that there might be an asymmetry between making ice and melting ice. It seems that on the planet, that's not the case. That is that if you go to a warmer world, ice melts and sea level rises much faster than it falls. And if you think of it, it's because gravity helps. When you're building an ice sheet, gravity is trying to cause it to collapse. When you're melting an ice sheet, gravity is very much helping it to collapse. So on these sorts of timescales, in a warmer world, you will inevitably end up with less ice and higher sea levels. So, recognizing that time is running short, just draw your attention to the fact that at the southern end of this circulation system, there are some regions of deep bottom water formation. I'm not going to spend any time on this because I know that Keith and others will take you through it, but there are some very specific mechanisms in the Antarctic to do with the production of sea ice and the drawing of warm water in under the sea ice as the dominant winds generate ice in these shore-based ice factories, reject salt and produce dense water that tips off into the abyss. But it's not just under the sea ice, it's under the ice shelves that important things happen. So if we zoom in, again, I'm not going to talk about the processes because there are others here who can do it much better than I can, but there are some very important and quite complex processes that take place under ice shelves, generating deep bottom water that goes off and chills 40% of the world ocean, but also causing rapid melting at the grounding line, which is pertinent to whether Mercer was right or wrong. And here's an Antarctocentric view of the global circulation system, which just shows the third dimension of depth and indicates the importance to the world ocean of the Antarctic refrigerator as well as the North Atlantic refrigerator for keeping it the way it is. And of course, any changes in behavior of those processes will have global consequences. So I'm getting towards the end of my pitch. The global consequences of regional polar warming are all to do with sea level rise, global ocean change, and the coupled impact on the atmosphere and climate. And indeed, if one looks at John Schellenhuber and others' so-called tipping point diagram, which is intended to show places in the Earth system which are vulnerable to internal dynamics taking over from an external tipping force, one finds that they've identified, I can't remember how many it is, what is it, a dozen or so potential tipping points in the Earth system, and it's no surprise to me that a number of these relate to polar processes. Right, what do you need to do to make progress in studying these processes? Well, if you want to look at the history of them, where the ice sheets were and where they flowed in the past, if you want to understand what the oceanography is now, if you want to understand what is happening to the ice sheet, its grounding line and its ice shelves now, if you want to understand what's happening to the sea ice, and if you want to understand what's happening to the biology, then you need to get into this hidden zone underneath the sea ice, which is underneath the ice or ice shelves, which is either very difficult to access if it's sea ice, or essentially impossible to access other than by drilling holes through the ice shelves when we're talking about ice shelves. So what lies beneath is the big issue, and this beast provides the UK community with a superb way of finding out. So Autosub under ice addresses key issues important to all of these major Earth system science questions. Here's a picture of the Ronnie Filchner ice shelf, this area which at present is well outside the range where we might expect collapse, but where there are important processes taking place beneath it as tides and currents squish water in to this cavity. The red dots show areas where Keith and others from BAS have drilled their way through the ice shelf to put instruments in at a point to try and figure out what's going on down there and then model it. The proposal with this beast was to get right underneath to some of the places where those key processes I was telling you about take place. It was only partially pulled off this time, but clearly the demonstration of the technical capability convinces that with a little bit more effort and perhaps a slight tinge of additional luck, this will soon be something which is meat and drink to the community trying to understand those processes. So I mentioned the International Polar Year, which kicks off at the beginning of next year. Autosub continues into the future. Hopefully it will be part of the great campaign to understand the polar regions better that will run from 1st of March 2007 to 1st of March 2009. IPY intends to lead a legacy of new instrumentation, new networks, which allow the polar regions to be monitored even more intensively in the future than in the past, and Autosub surely will play a role in that. And with that, people always ask me, have you got penguins in your talk? And so I always have to finish on this one. So yes, I have. So thanks very much.